We all live in the experience and illusion created by our brain, which functions as a neural computer with limitless imagination and remarkable capabilities. In this series, we'll explore the physics and mathematics behind this computing machine. Specifically, we're interested in the following questions. 1. How is information encoded, processed, and stored within the brain? This includes the details of brain I/O. How are various sensory inputs converted into neural signals? And how are neural signals converted back to outputs? What mechanisms does the brain use to process and store these signals? How does the brain access and retrieve stored information, and use it to synthesize novel outputs? 2. How do different parts of the brain communicate with each other? Considering the inability of any single neuron to exert remote control over its peers, how could billions of mindless neurons collectively produce coherent behavior without divine intervention? 3. How can the brain automatically recognize familiar patterns, develop internal representations, and learn from past experiences? Unlike the artificial neural network, our brain operates without distinct training and inference phases. No one could define a loss function, prepare the training data, and run the back-propagation algorithm for it. How could the system just learn by itself? Ultimately, we want a scientific explanation for the origin question. That is, how could nature construct and operate an universal computing machine without any help from a higher power or an intelligent designer? To illustrate how easy it is to construct and operate a neural computer, let us build a prototype that can factor integers in constant time. Integer factorization is to decompose a composite number into a product of prime numbers. It is an important problem in modern cryptography, as many encryption protocols depend on the difficulty of factoring large numbers for their security. No classical algorithm is known to solve integer factorization in polynomial time. In theory, quantum computers can factor integers in polynomial time. The algorithm was first proposed by Peter Shor in 1995. But the realization of Shor's algorithm requires specialized hardware and software. It took decades of research and development to build a state-of-the-art quantum computer to do integer factorization, and the scaling of the implementation remains a challenge to the industry. Let me show you a new computer architecture that has the potential to outperform both classical and quantum computers. We shall refer to this new computational model as neural computation, and any device that performs neural computation as a neural computer. At the fundamental level, a neural computer is an analog computer, or more accurately, a parallel quantum computer. However, both terms have been in use for ages. They usually mean something different from what's to be discussed here. For most people, a quantum computer refers to a quantum system that imitates the sequential computing architecture used in digital computers. While an analog computer is a special-purpose machine that uses analog signals to model a problem to be solved. Our brain is a distinct universal computer from any existing computers. To avoid any confusion, we will adopt the term neural computer. To build a neural computer, all we need is an ordinary string. Just tie the string to two fixed points. Voila! We've successfully built a neural computer that can factor integers in constant time. At this point, you might think I must be joking. How could this be a computer? It doesn't even have an input or output device. What on earth does this computer compute? Well, we're in a new paradigm of computing. You have to let go of your preconceived notions about computers, and approach computation with an open and fresh mind. First, let's see what exactly this machine computes. This machine computes whether or not an input number f is divisible by another number p, where both f and p are integers. The machine outputs a Boolean value, returning true if the input f is a multiple of p, and false if the input f is not divisible by p. Unlike classical computers, where information is encoded and processed in a series of bits, neural computers encode and process information as a set of discrete frequencies. In this neural factoring machine, the input number f is encoded as the frequency of a vibration. The vibration is generated by a mechanical wave generator on the left, which serves as this computer's input device. A neural computer can comprise any number of neural processors. A neural processor is any physical object that may resonate with a source vibration. This neural factoring machine contains only one processor, which is a string resonator with a fixed length. This particular string resonator has a natural frequency of 13 Hz, which corresponds to the value of the divisor p. Now, let's turn on the wave generator and observe how a neural computer operates. Currently, the wave generator vibrates at a frequency of 1 cycle per second. This effectively inputs the number 1 into the computer. The string moves with the wave generator, but nothing particularly interesting occurs. This corresponds to the output value of false or no, indicating that the number 1 is not divisible by 13. We can change the input by increasing the frequency of vibration. Most of time, the string simply mirrors the movement of the wave generator. When the input approaches the value of 13, a notable transformation takes place. The amplitude of the string vibrations increases significantly. Upon reaching an input value of 13, the string forms a standing wave, representing the activation of a neural processor. This corresponds to the output value of true or yes, confirming that the number 13 is indeed divisible by itself. As we keep increasing the input, the amplitude of the string's vibration diminishes, causing the standing wave to vanish. This corresponds to the deactivation of the neural processor, signifying that these numbers are not divisible by 13. When the input turns into 26, the string once again forms a standing wave, serving as an indicator that 26 is a multiple of 13. As we raise the input from 26 to 39, the same pattern repeats. The string always forms a standing wave whenever the input is a multiple of 13. Therefore, the activation and deactivation of a neural processor can model a Boolean value, representing whether an input frequency is a multiple of its natural frequency. To test an input's divisibility for more numbers, we just need to connect the input to more processors. For example, in this setup, the wave generator is attached to 2 string processors, each with a unique natural frequency. When both strings resonate with the input frequency, signified by the presence of 2 standing waves, we know that the input frequency must be divisible by both resonators' natural frequencies. To factor large numbers, we just need to build neural computers with lots of processors, each corresponding to a potential prime factor. A neural processor can be made of any physical objects. For instance, a closed string makes a good resonator. So does a wine glass. Here, the physics girl Dianna Cowern unknowingly operates a neural factoring machine. She performs the same computations as our string-based prototype. In this particular setup, the input is encoded as the pitch of her sound. Her vocal cords function as the input device, while the wine glass is a resonator. The activation of the resonator leads to the breaking of the glass, which is the output of this neural computer. This setup has a subtle but important difference from the string-based prototype. The input is not transmitted to the resonator via direct physical contact. Instead, it is broadcasted to the resonator through open air. This open architecture allows us to build a neural computer with an enormous number of resonators, supporting massive parallel processing. In fact, rock stars such as Freddie Mercury have already done a proof-of-concept study for us. Imagine that. Each fan in the concert is given a resonator that resonates with a unique prime number. Whenever Mercury shouts out a note, the frequency of this note corresponds to the number to be factored. Each fan then looks at the resonator. If it resonates, the fans will shout out the number on their resonator. This way, everyone in the concert can immediately know the factoring result. The time to compute such a result is determined by the speed of sound and the size of stadium. It doesn't take longer time to factor bigger numbers. Therefore, our stadium-based neural computer indeed solves integer factorization in constant time. If we zoom right into the inner ears of each fan with electron microscope, there lies the opportunity to further scale up our solution by several orders of magnitude. There are rows of minute hairs only a few thousandths of millimeter high. They are listening to specific frequencies, and ready to dance when the right vibration arrives. This massive array of resonators demonstrate that nature has long mastered the art of constructing and operating large-scale neural computers. Let's take a break, and recap what we have learned so far. A neural computer is nothing more than a network of computing nodes. At first glance, this neural network looks like an artificial neural network without any hidden layer. However, there are some key differences between these two models of computation. Artificial neural networks run on classical computers, which are made of hardware components carefully designed by human creators. All hardware components must be wired together precisely. Otherwise, the entire system wouldn't function. Additionally, artificial neural networks depend on a host of system and application software, which have to be carefully coded and tested by human creators. The successful development of artificial systems requires meticulous human care. As the saying goes, garbage in, garbage out, highlighting the importance of high-quality training data and human guidance. In contrast, neural computers are made of ordinary objects. They can be wired casually and organized into a variety of configurations. Neural computers don't require any system or application software to operate. Their operation relies only on the universal phenomenon of resonance. Because of the flexibility and open design, objects can just self-organize into neural computers, spontaneously processing arbitrary input, and producing meaningful output for those who can properly interpret the result. The input node, labeled as F, is a peripheral device that transfers information into the network. Within the network are the base computational units, known as resonators or neural processors. Resonators play a crucial role in neural processing. They can relay, transform, and store signals. Each resonator is identified by a unique number, which corresponds to a resonator's natural frequency. Do not confuse these numbers with the weights found in artificial neural networks. They're not modifiable variables in classical computers. Rather, they're immutable properties of the underlying resonators. In a neural computer, data are encoded as a set of discrete frequencies and they are transmitted and stored in the form of specific vibrations. To input a number into the system, one just needs to shake the input node at that frequency. The vibration propagates over the network, activating resonators when the input frequency is a multiple of their respective natural frequencies. The resulting activation pattern represents the output of neural computation. If we shake a particle at 20 to 20,000 cycles per second, it produces audible sound signal. To factor big numbers, we just need to shake it faster. If we use ultrasound to compute, we can operate neural computers at millions of cycles per second. If the input node carries any charge, the oscillation results in electromagnetic signals, which allows us to operate neural computers at a much higher frequency. If we shake charged particles at 400 to 800 trillion cycles per second, the vibration becomes visible light signal, whose resonators can be as small as an atom. In fact, there are so many tiny resonators in your eyes and ears, enabling you to see and hear my messages right now. They're busy converting light and sound signals to neural signals without any supervision or guidance from you. To understand how neural signals are processed inside our brain, we must first comprehend a different form of oscillation and resonance. Our brain consists of approximately 100 billion interconnected neurons. On the cell membrane of neurons, there are two types of membrane proteins. Ion pumps use the energy of ATP hydrolysis to facilitate the transportation of ions against their electrochemical gradients. Conversely, ion channels facilitate the passage of ions across the membrane down their electrochemical gradients. The movement of charged particles generates cross-membrane current. Because all ion pumps and ion channels move in perpetual motion, two opposite actions cause the fluctuation of membrane potential. When a neuron is at rest, its membrane potential oscillates around some equilibrium level. An external stimulus may cause a sizable disturbance of local membrane potential, much like an external force causing the vibration of a classical object. Due to the Brownian motion of ion pumps and ion channels, the disturbance of local membrane potential dissipates over time. The process is analogous to a mechanical vibration damping in the absence of an external force. When multiple stimuli occur in different areas, the dispersion of ion channels and ion pumps creates complex interference patterns. If the disturbance of local membrane potential exceeds certain threshold, it activates a large number of voltage-gated ion channels, triggering a sustained action potential, the equivalent of a standing wave in our string-based prototype. In our previous series, Quantum Mechanics Reimagined, we've worked out the physics and mathematical formulation for computing the membrane potential triggered by a given input signal. If you haven't had the chance to watch the series, or find it hard to wrap your head around this complex equation, don't worry. For now, we just need to develop some physical intuition, getting a basic sense of how information is processed by a neuron at very high level. Imagine an ion pump or ion channel continually moving in one direction. They would eventually circumnavigate around a neuron, and their paths would form some kind of loops. This equation just tells how to add up all these paths, and calculate the density of ion crossings at each and every point in spacetime. The sum over all possible paths results in a probability wave propagating on the finite surface of a neuron. At high level, a neuron would function as a circular resonator, behaving like how this mechanical resonator reacts to the disturbance caused by external forces. A circular resonator is a string with a fixed length. Only disturbances of certain frequencies can trigger standing waves along this type of structure. Another example is how atoms process and generate light signals. Light is caused by the oscillation of electric charges. When the oscillation has to be confined within a finite space like an atom, only certain frequencies trigger standing waves. These standing waves represent some stable states of the atom, corresponding to some distinct energy levels. When atoms transition from one stable state to another, they absorb or emit photons that encapsulate the energy between these two states. The amount of energy encapsulated in a photon is proportional to its frequency. The higher the frequency, the more energetic the photon is. Therefore, an atom, at its core, acts as a resonator for light signals. No one on the Earth would ever consider a snow mountain as an information processing system. But, imagine yourself an alien physicist on a distant planet. You just invented a powerful telescope to study the snowpacks on the Earth. Due to the vast distance, your observation has very limited spatial and temporal resolution. You can only detect a mountain as a point particle, and a snowfall or avalanche as a single event. To you, a mountain looks like an atom, and the environment appears as empty as a vacuum. A snowfall is akin to absorbing a photon, while an avalanche is analogous to emitting one. The occurrences of snowfalls or avalanches seem random and hard to predict. After a large number of observations, you discover that not all snowfalls are created equal. While a heavy snowfall triggers many avalanches in a short period of time, it takes many light snowfalls to create a single avalanche, and sporadic flurries may never cause any avalanche. Each snowfall travels like a particle, but they can interfere like a wave. When multiple snowfalls overlap, they interfere positively, triggering lots of avalanches. What puzzles you most is that each mountain seems to produce a unique set of distinct avalanches. Increasing snowfalls produces more avalanches, but it doesn't really change the characteristics of each avalanche. To a distant observer, these constitute mysterious quantum behavior that requires the heavy machineries of modern physics to understand. But to an observer on the Earth, they're simple phenomena, easily explicable. The triggering of avalanche is a nonlinear process, similar to the firing of action potential by a neuron, or the emission of photon by an atom. A snowfall dumps snowflakes on a mountain slope, transitioning the system to different energy states. The snow accumulates over time. When the system becomes unstable, an avalanche is triggered, returning the system to a stable state. An avalanche can be characterized by a frequency number, which is defined as the amount of falling snowflakes divided by the duration of the event. This frequency number quantifies how energetic an avalanche is. For a particular mountain slope, the energy released per avalanche and the duration of an avalanche are largely a function of its terrain structure and the overall system environment. Given a system environment, including a stable thermal environment and a fixed gravitational field, a mountain slope outputs only avalanches of specific frequencies. Please note that this frequency is different from the rate of occurrence of avalanches. An avalanche's frequency is equivalent to a photon's frequency, or the temporal density of ion crossings encapsulated in a neural signal. A photon's frequency is perceived as the color of light. We may refer to this frequency as the color of an avalanche, or the color of a neural signal to avoid the confusion. We can use the same definition to characterize a snowfall, and use its frequency or color to measure its energy level. From the perspective of information processing, a neuron behaves like a complex mountain system. Incoming signals release neurotransmitters onto this membrane structure, much like snowfalls depositing snowflakes onto mountainous areas. Each neurotransmitter activates a cascading chemical reaction, triggering a mini-avalanche of ion crossings. These mini-avalanches propagate on the membrane of postsynaptic region, creating complex interference patterns. Sometimes, the interference creates a local avalanche big enough to trigger a global avalanche. A global avalanche is so energetic. Once it's triggered, it can travel from cell body to all axon terminals, releasing neurotransmitters onto similar membrane structure of downstream neurons. The same process repeats, allowing neural signals to propagate throughout a neural network. The propagation of neural signals creates unique activation patterns, which serves as the output of the neural network. The signal propagation continually transforms input signals into output signals. This simple computational model is the essence of neural processing. Let's see what happens if neurons start to make random connections to their neighbors. Suppose that there are 4 separate neurons in your nervous system. P0 and H0 are 2 sensory neurons. P0 is a photoreceptor in your eyes, while H0 is a hair cell in your ears. C0 is a neuron in your central nervous system, and M0 is a neuron in your laryngeal motor cortex. During your brain development, they all extend their axons, making random connections to their neighbors. Here is a cute cat, Schrödinger. You like to call him by his nickname Dinger. Dinger loves walk around. Whenever you see Dinger in front of you, neuron P0 is activated, sending a neural signal to all its downstream neurons. P0 is just an ordinary photoreceptor. It can be activated when you see many other things. But one of its downstream neurons, P5, gets activated, if and only if Dinger is present. So P5 represents some unique visual feature of Dinger. In other words, if P5 is activated, it indicates that Dinger is in your sight. Similarly, when Dinger makes a distinct sound, neuron H0 get activated, sending an auditory signal to its downstream neurons. Neuron H6 is activated, if and only if Dinger is meowing. So H6 represents a unique auditory feature of Dinger's sound. Neuron M0 makes lots of connections to the muscle cells on your vocal cords. To figure out what it does, we insert an electrode into your brain, and stimulate neuron M0. Whenever M0 is triggered, you always utter the word, Dinger! So M0 represents your muscle memory for uttering the word, Dinger. When we poke C0 in your central nervous system, no obvious action is observed. We don't really know what the network in your central nervous system does. In a central nervous system with billions of neurons, each with tens of thousands synaptic connections with their neighbors, there will always be some paths between any 2 neurons. Let's assume P5 grows a connection to C0. H6 forms a link with C1. And C3 establishes a path to M0. Let's re-examine what happens if Dinger walks into your sight. First, the visual input triggers a neural signal at P0, which subsequently activates P5. The activation of P5 sends the signal down to C0. Let's suppose that C0 is also activated, broadcasting Dinger's presence to all neurons in its downstream network. If C1 is always activated by Dinger's presence, its activation becomes another internal representation of Dinger. Because of the connection from H6 to C1, the signal triggered by Dinger's distinct sound can also reach and activate C1. Thus, the activation of C1 is actually not tied to any particular modalities. It is a higher-level abstraction about Dinger that can be triggered by both visual and auditory input. Now, let's explore what happens if C1 grows a connection to P5. With this new configuration, a signal originating from C1 will activate P5, reach C0, and then loop back to C1, resulting in a circulating signal. The signal may continually circle along this neural circuit even if dinger is no longer present. Hence, the circulating signal represents your memory about dinger. The closed loop forms a neural circuit, which functions as a circular resonator. If a neural circuit resonates with an incoming signal, it can retain that signal in the form of a standing wave. Neural circuits are the building blocks of neural computers, with resonance being the only primitive of all neural operations. If you see and hear dinger often, the circulating signal will become the running average of dinger's visual and auditory representation. As the signal continually circles around, it releases neurotransmitters along the neural circuit. This keeps all the neurons along the circuit at an elevated energy level, effectively lowering their activation thresholds in response to both visual and auditory signals triggered by dinger's presence. In other words, you're more attuned to dinger's image and sound, becoming more attentive to him. So this neural circuit can not only refine and store your memory about dinger but also change your behavior by learning from your past experiences. So neuron C0 periodically transmits the circulating signal to C3. But when the signal reaches C3, its energy level is too low to activate C3. This is the reason why, in typical circumstances, these circulating signals don't reach downstream motor neurons, accidentally turning random thoughts into garbled words uttered loudly. Suppose that you haven't seen dinger for a month and you miss him very much. Every time you think about dinger, it has to activate some neurons along this neural circuit because the circuit is the physical embodiment of dinger in your mind. As days turn into weeks, these tiny thoughts are converged into a resonating signal. The signal becomes stronger, and the circuit becoming hotter. Suddenly, you heard a sound. This caught your attention. The usually weak signal from your auditory system merges with the circulating signal, triggering a gigantic avalanche that cascades down each and every neuron along this super-hot circuit. When the signal reaches C3, it is still so powerful that it can pass C3 and activate M0. And then, we heard you cry out, "Dinger!" You have successfully retrieved your muscle memory for uttering a specific word, and sent the signal to the muscle cells on your vocal cords, faithfully reproducing the intended sound. So the attention is the manifestation of an energetic wave carrying some local signals across the network. The passing signals will be ignored by non-resonating circuits, but picked up by resonating circuits for further processing. Communication within a neural network mimics the dynamics of a trading pit. Amid the chaos, individuals shout, yell, and gesture over one another. Despite the apparent disorder, it still manages to get most of important business done. That's how neural computers communicate and operate in a nutshell. I hope, after your brain processes this visual input, it could produce an intuitive understanding that would circulate in your mind for a while. Next, we will focus on more technical aspects of neural computation. For example, how does our brain store and synthesize complex signals, including everything that we can see, hear, and imagine? If you find the content in this channel is interesting, please click the like button below, subscribe, and share it with your friends. It will help to connect those who are also interested in the topic. Thank you very much for your help.